Hi everyone, in this video we're going to talk about different ways of calculating integrals of a vector field. There are two kinds: line integrals of a vector field, surface integrals of a vector field. So if you're looking at these problems, line integral of a vector field, and the next group will be the surface integral of a vector field. What is the first thing we have to do? And if the answer is yes or no, then what other options do we have for depending on answer is yes or no? In this chart, it seems like there's not much to do if the answer is no, and so on. Right, just remember that if it is a line integral, it's all about curl. If it is a surface integral, it's all about divergence. So you have some better options if you have a curl 0. If not, you don't have much option. If your vector field of this, I forgot to mention that this discussion is particularly for not necessarily closed loop, but it still applies to the closed loop. But if you start at the one point and ending at a different point, if that's a general case like that, and if your curl is not 0, take the curl. Not 0, it doesn't matter. If it is in the two-dimensional space or curve sitting inside the three-dimensional space, this goes exactly the same on here. I think I'm talking about two-dimensional case. Make sure, I think it's two-dimensional case, but it goes exactly the same, so I may have to skip that part. But here is a two-dimensional case. Curl is non-zero. Then take that parameterization and put that parameterization in there, turn it into one variable dt integral, and go ahead and calculate that integral. That's all you've got. But if the curl is 0, interesting thing is happening, and that's what we're doing next time. So if the curl is 0, what this means is that it's likely for that, especially for those loop that starts at one point and not necessarily ending at the same point, most of the function, we look at it here, that what that means is you can find the gradient vector field that matches these vector field. So there's a scalar two-variable function. If you take the gradient, it'll become that vector field you're looking at in there. That's what it means. And if it is easy to find that vector field, then you have one answer. If it is hard, then, or if you don't want to find it, and then there's the next case. If it is easy, very simple, if you feel like you can find it, what that means is that this line integral is going to be fb minus fa. This is sometimes called the fundamental theorem of line integrals. Now, if it is easy, you have that scalar function. In physics, we call this a potential function. So you have a potential function evaluated at there minus potential function of evaluated there, and that's that. It involves a little bit of calculation. But suppose it looks messy and you don't want to find that integral, the potential function. What is your choice? What you can do if the curl is 0, still in the curl is 0, you can replace this path with something slightly simpler. Either it's a straight line or part of ellipse, something that parameterization is the standard, or if you're asking you to go around in straight line and go around straight line in here, you can see in that case, let me use this thing over here. If the curl is 0, and if their path is like really inconvenient like that, that involves 3 different parameterization because it's kind of not smooth, then you can just replace that with one straight line in there and use that parameterization to calculate the line integral. You can only do that if the curl of the vector field you are calculating is 0. All right, those are the chart. And if you think about it, it's all about curl 0. It is not that complicated. Maybe it is. You have to just think about it a couple of times and practice. Here I'm looking at the problem of computing line integral. What should I do? This part, you just have to be careful with this replacing these things. This is relying on Green's theorem. So for example, if you are looking at the path going from A to B, that is a gamma we're talking about here, and gamma 1 happened to be down here, right? Let me replace it with something simpler, like straight line. That's a tendency that we wanted to replace it with a gamma 1. Now we're applying the Green's theorem to this region with this opposite rotation and things like that. So it requires the vector field F is defined nicely in this interior region. Even though it defined just fine on regions around this gamma, go ahead and change that to yellow with the gamma like that. If the vector field is defined all in that, and this original problem itself is defined nicely. And secondly, if it is defined nicely on this part right there, and this line integral is defined right there. But sometimes you're going to find that these two line integral will not be the same, even though it seems like I claimed it's the same. It only happens if we just miss that part right there. And around the neighborhood of these gamma 1 path, the vector field is just fine. Around the neighborhood of a gamma 1 path, vector field is just fine. But somewhere in between this gamma and gamma 1, if that makes sense, just like in that picture, if the vector field is not defined right in somewhere in there, then you cannot apply Green's theorem to this loop. Let's say negative gamma plus this gamma 1, in that case, is oriented counterclockwise to this region formed by these two curves and gamma 1. We cannot apply Green's theorem to that part. So this whole thing is relied on the Green's theorem so that you can replace this thing. But there are sometimes vector field is undefined in there, but still it turns out to be the same. That's something, different discussion. So in this part, you have to make sure that you have to check that the curl of this vector field is defined everywhere, kind of in between the gamma original 1 and your preferred path, the gamma 1, in a good neighborhood, not missing anywhere interior part. If that happens, then you can go and replace it. In particular, if your vector field is like polynomial, no log or square root or denominator or anything, just made out of typical functions that is defined everywhere, then you don't have to worry about any of those. You can replace whatever type of path you want. Second one is still taking place in two-dimensional space, but this time we're looking at the curve that starts and closes in the same place, and it doesn't self-cross or anything. It creates nice region inside. And here you have to be careful. This time you really have to check the vector field is entirely defined inside that region enclosed by the surface. If so, the rest of the part holds. If not, then you have to just calculate honestly. Put the parameterization of C and go ahead and do this dt calculation. But again, the question we have to ask, and which opens up a different possibility of calculation, is this curl. Is the scalar curl of this two-dimensional vector field, is the curl is 0? And if it is especially yes on this entire interior region, if that holds, then the answer happened to be simple. Answer is 0. If this is because of the Green's theorem. This, if it closes up like this, Green's theorem applies, even though the earlier one, all this thing, especially this option in here, is actually a consequence of Green's theorem. But Green's theorem here allows you to do it easier, and you don't have to calculate potential function or anything. This is going to be 0 because Green's theorem is the double integral of a curl. The curl is 0 is 0. Only for that. Closed curve. Now next part is realize exactly the same thing, but it is all happening in three-dimensional space. So here we're looking at line integral over path starting from A and ending at B, not necessarily the same beginning and terminal points. And here's my XYZ space indication. The thing is the same. There's the same curl we're doing, but it involves more components. Curl is not 0. Not much you could do. go ahead and plug in this parameterization you have. Don't change anything. Honest calculation what you have. Now if the curl is 0, now you can think about finding this potential function once again. This involves a lot more calculation. It's not just about x and y separately, and x and y are mingled together. So I find that this is a far harder partial differential equation is involved in here. So often people don't look for this potential function in there, but if you can find that potential function, of course your answer is the value of the difference of this potential function. There's still fundamental theorem of line integral. Now most of the time you're not going to try to find that. It's usually complicated. So what is the option we have in there? Again, you can go ahead and replace that with a simpler path. It's the same reasoning as before it was because of the Green's theorem, is because of the Stokes theorem. If you just go around like this and close up the surface, and that is going to be the same as surface integral over that surface S. But the vector field, the changes to curl is 0, so that's going to be 0. So you can replace that. This is particularly powerful, especially in the three-dimensional space. So if the curl is 0, again, you can replace the path with whatever is easier, and then you can use that parameterization of that replaced path to calculate the line integral. The line integral value will be the same. Okay, those are discussion about line integral, and I have forgotten to put this line integral that closes up like this in three-dimensional space, but answers are similar to the earlier one. I'm going to pretend this is three-dimensional case. It can be three-dimensional case, starting here and wobbly like that and close up like this. But it's not too complicated, so that we can see this close up into a nice surface, and then Stokes theorem applies. If the curl, not the scalar curl, the curl is 0, then your integral, the line integral will be simply 0, because, and it should be defined on some sort of surface that closes in. You don't have any option if it is two-dimensional. You have to close it in really one part. But think about three-dimensional space. Suppose, for example, you have this loop hovering in three-dimensional space, but your vector field have a little problem right in the middle of the part, but you can still go ahead and branches out and use these different surfaces in here. If that's okay, if that's the only part that is not defined, then you can use that surface to apply the Green's theorem. Then everything is good. So it's interesting, slightly more interesting thing is going on with the Stokes theorem than in Green's theorem. But sometimes you can find loop like this. That's a loop in there. It closes up. But not only it defines in one point in there, this entire point is a vertical line like this to the infinity. All this point, the vector field is not defined, and you can see there is no way to close up this surface with this C as an edge so that we can apply Stokes theorem. There's a problem in there. If that's the case, you're not going to be able to do what this one is saying in there. So if the curl is 0 and where the vector field is not defined, is not that like infinitude, then you can use this crazy surface that avoids that problem part, and then you can still apply Stokes theorem and get this conclusion that it's going to be 0, because Stokes theorem is a surface integral over curl. So that's going to be curl equals 0. So those were the discussion about the line integral. Next part is going to be the surface integral, for which you have to use divergence theorem. Again, if you're looking at random line integral problem, the first question you have to ask is, what is the curl of this vector field involved? Now, if you're looking at top surface integral of random surface integral, first thing you have to calculate is the divergence. From there, your path of calculations changes. So here it is. Let me start with this setup. This is a surface. It doesn't close up. It has edges in there. And this edge is supposed to be a curve and is oriented And this orientation together with this where the normal vectors are facing. If there's a surface in there and there's a normal vector facing this way, then curve must go around like this right-hand rule like that. If this is a setup, and if you're looking at the surface integral of a vector field f, first thing you check is a divergence. It's particularly easy to remember. Px plus qy plus rz. Is this 0? No. If it is not 0, then you have no other options. Take the parameterization of the surface and go ahead and do this honest calculation with this 2-parameter st and change that surface integral into what is it called? A double integral with the parameter st plane. But if the divergence is 0, then there's a good news. This can be turned into, what is it? Divergence theorem becomes a triple integral. If you think about imaginary surface underneath it, it closes up into that. So what that allows us to do is that, all right, what that means is the vector field that you're looking at, if the divergence is 0, locally, if it is defined everywhere, and then locally, this is going to be curl of something. Before, in the line integral case, if the curl is 0, then it was a gradient of something. And what this allows us to do is that if the divergence is 0, just locally, but in many cases, in entire space, this means it's a curl of something. So gradient of something versus curl of something, that's the analogy I'm making. So that vector field that you're looking at divergence 0, you know it's locally curl of something. Okay? So calculating this curl, in my opinion, it's fairly complicated. But if you know that is the answer, and if you have this phi vector is a capital phi, then this is going back to this Stokes theorem, interestingly enough. And you're looking at this curl of phi, that you can replace the capital F with the curl of phi, and this S happens to be the surface that appears in the Stokes theorem, so you're going backward. This is like a fundamental theorem of a surface integral, maybe, the not line integral. But I think I said something wrong. So let me take that back. But this is truly Stokes theorem going backward. Get here, that's the C going around like that, and surface is there. This vector line integral of that is a curl of that phi that we happen to be able to rewind it. In that case, you go ahead and calculate this line integral with this curve C. I don't know if that's going to be necessarily easy or not, but just something to remember. There's this option. Often is can't really calculate this phi, this different calculation. So this will be most more realistic thing for our courses. It's the following: if you know it's a curl of something, it's whatever is happening around it here, then you can replace that surface with something simpler. If it can be like a flat surface, that's great. If it can be easier to parameterize kind of thing, such as sphere, that's even better. So you can replace that surface with something simpler and easier. Still have to be upward, but it must have the same edges of the surface. In that case, you can calculate the surface integral with a simpler surface, and it's just a magic, right? So that's the situation, that's the options you have. So the following is a simple corollary of what we have gone through. It's better if you happen to be looking at the surface integral of a surface that doesn't have edge, it closes up like this, and enclosing a nice solid where nothing, I forgot to put in there, but it has to be divergence on entire interior of this solid W. And this one is indicating the surface boundary. That's a boundary notation, not partial differential notation. If the divergence is not 0, no choice, take this parameterization of the surface honest one and calculate this double integral for in the ST plane. That's all you have. But if the divergence is 0, and if it's closed up like this, that's a direct application of the divergence theorem. This surface integral is equal to triple integral of a scalar function divergence, but that divergence is 0, so this surface integral must be 0. So that's the case. So this is usually considered as a difficult surface integral problem, usually because students didn't see this following path. If you happen to have a divergence 0, then you can replace that surface, keeping the edges, with a surface something simpler or something easier to parameterize. Then you can integrate that surface over that surface, and then it'll give you the same answer. Only if your divergence is 0 in the region that's surrounding this surface, if that's the case. Or if you have to use that one, actually, in between this S1 and S, whatever is in between in there, it has to be all defined. Otherwise, it's because it uses a divergence theorem that requires these two different surfaces between S and S1, there shouldn't be anything in there, anything undefined. So I don't know what to. That's a very specific condition. So you have to be careful when you go from S to S1. Make sure your vector field is simply defined everywhere. Then you don't have to worry about anything. Right? This is actually very practical advice that is going to be useful. And I haven't seen this is all summarized into the chart like that anywhere. But I find it is really useful, not only to calculating these surface integrals or line integrals, but in terms of understanding relationship between these things. It actually helps you to see the bigger picture and the theoretical, helps you to have a better theoretical understanding on this subject. Thank you and good luck in learning this subject.